Okay, welcome everyone to the industry session. We are very fortunate to have several fantastic talks. To kick things off, we're gonna figure out what to do about the problem of memory-unsafe languages. So I feel like at PLDI we already know the answer. It's use a memory-safe language, duh. But the reality is there's billions of lines of code that aren't going away. And so we have to figure out how to gracefully make this transition and have things work together. And it's an incredibly hard challenge. So Yeoul's going to tell us about work going on at Apple to make that happen. Let's welcome our speaker.
Thanks so much. Thanks, Zach, for the great introduction. Hi, my name is Yeoul, and I work in languages and runtimes at Apple. Our group works on things such as programming language design, compilers, and related technologies and tools. Memory safety in large code bases is not a solved problem. Large programs usually include code written in multiple languages. This means that achieving memory safety for a whole program requires safe interoperability between multiple languages, especially between safe and unsafe languages. In this talk, I'll discuss some of the open problems that we'd love to see more research into from this community. And I'll talk about the work that we've done with Swift, which we think will be generally applicable to other languages. Over the last decades, memory safety bugs have accounted for about 70% of the severe security vulnerabilities across the industry. Even today, attackers against security-sensitive systems are mainly targeting memory safety vulnerabilities. You might be wondering why memory safety is still an issue, and Zach already talked about it. Haven't we solved this problem yet? In theory, yes, there are memory safety languages, such as Java, Rust, and Swift. Using languages like these remove most of the memory safety issues. However, in practice, no, the problem hasn't been solved yet. The problem is that there are billions of lines of C code in C and C++ code in production, and only recently people have seriously started adopting memory-safe languages in some of those large code bases. For example, the Linux kernel has been written in C as the main language since 1991. And the Rust for Linux project was created in 2020 to add some new code in Rust. However, as of today, the Linux kernel still has 96% of the C code and 0.1% of Rust. In fact, it has more Perl scripts than Rust right now. Large code bases like that cannot be rewritten in a new language overnight. A large number of the maintainers have been writing in C and or C++ for decades. So there can be a learning curve and some resistance to switching to a new language immediately. Even after the maintainers overcome that barrier, because of how the languages are different, switching may require major restructuring, significant testing, and qualification efforts. Please note that it's not specific to a certain language. This is a general challenge in adopting a new language in existing large code bases. Instead of rewriting everything all at once, gradual adoption allows you to start small and build over time. The common approach to gradual adoption in large C and C++ code bases, such as the WebKit browser and the Linux kernel, involves writing new code in a safe language or rewriting some security-critical components in a safe language. However, gradual adoption only works if the safe and unsafe languages can interoperate seamlessly. Here, interoperability means calling a C or C++ from a memory-safe language, calling a memory-safe language from C or C++, or using data structures defined in the other language. In this setting, safe interoperability is crucial. Otherwise, memory safety will be compromised. And we think safe interoperability is a very rich topic for research. Especially, I want to call attention to 4 different problems here. Let me go through each of these in order. Consider a C function like filter image that takes a pointer and the size of an image. And imagine a safe language calls this function. That already sounds a bit unsafe, but there's a way to use this C function correctly. For example, by passing the correct size. But these requirements are not encoded in the type system in C or C++. So the safe language doesn't know how to use it safely. As a result, there's nothing preventing the safe language from using it incorrectly. For example, by passing a size that's too large and causing an out-of-bounds memory access, or by freeing the memory while the C function still holds the pointer for later use. Then there's a problem of reasonably inferring those expectations. That will require pointer analysis to understand all aliases of the pointer and how they are used. However, pointer analysis tools for C and C++ are not yet up to the task due to the difficulty posed by undefined behavior and implicit assumptions inherent in these languages. Even if those expectations can be inferred at the language boundaries, enforcing them within C or C++ itself is challenging. This is because these languages lack abstractions to enforce safety properties, such as bounds of memory, how long this memory is valid, and who owns the memory. While C++ provides some more abstractions than C, they are still not comprehensive enough to guarantee whole program safety. And because unsafe languages like C and C++ don't explicitly express the expectations and requirements, formal reasoning about systems composed of safe and unsafe languages is challenging. It's important to ask and answer questions like, is the end-to-end system still memory safe? And how to ensure memory safety problems must be due to unsafe code. While many of those issues remain unresolved, there has been a lot of ongoing research in this area. And we've also done some work in the context of Swift. I'll talk about how we approach these problems. Swift is a memory-safe and cross-platform programming language. It's statically compiled and has a small runtime, so it provides good performance for systems programming. Swift is designed to support incremental adoption in existing C or C++ code bases. Its compilation model allows direct calls between Swift and C or C++. That is, the Swift compiler can export a Swift interface as a C or C++ header, allowing C or C++ code to directly call a Swift function. Similarly, Swift can directly import C or C++ headers so that C or C++ types and declarations are interpreted as if they are written in Swift. For example, this C function is imported into Swift exactly as if it were declared like this in Swift. Swift has historically imported C pointers using unsafe types. In this example, the image pointer is imported as an unsafe mutable pointer. In Swift, these unsafe pointer types are just as unsafe in Swift as they are in C. And this unsafeness is a general problem that arises whenever any unsafe language needs to interoperate with C or C++ pointers. So, Swift has recently introduced a safe pointer abstraction called span. Span is a safe view of contiguous memory owned by others. Span guarantees bounds safety by tracking the bounds information and performing bounds checks at memory accesses. It also guarantees lifetime safety. SWIFT enforces that spans cannot escape the immediate context or cannot be used beyond the lifetime of the objects they depend on. Ideally, a C pointer should be directly imported as a SWIFT span. That will make the interoperation boundary safe. But the problem is that C and C++ pointers are missing bounds and lifetime guarantees. To close those gaps, SWIFT's strategy is to allow programmers to express bounds and lifetime requirements for C and C++ code using annotations. Then SWIFT understands these annotations and uses them to import C or C++ code as safe SWIFT alternatives. There are many annotations for C and C++ code that SWIFT can understand now. But when it comes to pointers that do not own their memory, there are largely two groups of annotations. First, there are bounds annotations that turn the annotated types into dependent refinement types that depend on other values that contain the bounds information. This work is inspired by the academic work on the deputy system that was published in 2007. Additionally, there are some annotations that provide a concise way to express the lifetimes of memory. And these same annotations can also be used to enhance safety in C and C++, which I'll cover later in the talk. Here is an example of annotations that SWIFT can use to import pointers as SWIFT spans. The counted by annotation expresses the bounds of the underlying memory. In this example, the counted by image size on the image pointer means the pointer has at least as many elements as image size. No escape annotation is a kind of lifetime annotation. It indicates that the function doesn't keep the pointer after the function ends. This annotation is necessary to preserve the invariant of span that it must not be used after the underlying memory has been deallocated. By adding these annotations, SWIFT can understand the expectations and requirements for the C function. As a result, the function can be safely treated like a SWIFT function that takes a span directly. That way, SWIFT code can directly pass a span type to call the C function without using unsafe types. Behind the scenes, the compiler takes care of correctly extracting the pointer and the size from the span. So there's no possibility for a programmer to make mistakes. And the SWIFT code must use the C code correctly. However, manually adding all those annotations is a lot of work. So it's important to reasonably infer them automatically. There's a body of research about inferring bounds, but more research is needed to infer other safety properties. And even inferring bounds is not conclusive. While securing the boundary is a good start, we don't want to ignore the fact that as long as C and C++ remain unsafe, bugs there can override the safety guarantees made in the safe language and at the boundary. There have been many mitigation techniques for C and C++, but they haven't been sufficient to stop attackers from exploiting remaining bugs in that same category. Therefore, techniques that eliminate entire classes of bugs are incredibly powerful. They direct attackers to focus on exploiting different categories of bugs that are harder to exploit. Additionally, when investigating exploits and bugs, These techniques enable us to focus on the main classes of bugs that are not protected yet. To achieve this, Apple developed a new extension for C that guarantees bounce safety. This extension uses the same bounce annotations that are used for safe interoperability with Swift. The bounce safety extension is similar to Deputy, again, prior art that uses a dependent type system for bounce safety. However, our noble contribution lies in the combination of dependent types at the interoperation boundaries and the use of white pointers everywhere else. White pointers are automatically carry bounce information, so this approach makes it easy for programmers to grasp the programming model and reduces adoption burden, while still maintaining gradual adaptability thanks to dependent types at the boundaries. Here is a high-level overview of the bounce safety extension. The compiler guides programmers on where it needs more bounce information through diagnostics like this. Then the programmer can add bounce annotations there. And then the compiler inserts bounce checks on memory accesses using that information. This technique eliminates direct bounce safety problems in C code. The bounce safety extension has been adopted in millions of lines of production code at Apple. Based on our adoption experience, its performance impact on the whole operating system was negligible. The extension is open source, and our goal is to standardize the programming model in C. For this, we have recently started engaging with the C Standard Committee. Okay, let me recap. Safe interoperation between safe and unsafe languages is crucial for memory safety in large code bases that are historically written in C and C++. There are still lots of open research problems in this area, and we've only started tackling some of the problems in practice. I've talked about bounce and lifetime annotations to describe requirements in C and C++ code, but there is more work to do to support more language idioms and other safety properties. Reasonably inferring the requirements for C and C++ code is still an open problem, as pointer analysis tools for C and C++ are not up to the test yet. I've talked about enforcing bounce safety for C using the same bounce annotations, but enforcing lifetime safety and other safety properties is much more challenging. Formally reasoning about safety in mixed language settings is still an ongoing research topic. Additionally, designing the interoperability feature so that it's simple to use and fast to adopt is crucial for large-scale adoption. This helps avoid programmer mistakes that can turn into a security problem. Swift approach to directly importing a pointer as a span by using annotations helps with this. But there are still many other language idioms to support. If you found those problems interesting, Swift is a great platform to start. It has a large open source community and builds on Clang and LLVM. We are hiring summer research interns every year. We have a sponsor table over there, so please come talk to us about research collaborations. You can also find us online in LLVM Memory Safety Working Group and Swift forums. Please also check out the safe interoperability documentation in the URL at the bottom. Thanks for listening.
Okay, great. I think we have time for a couple of questions. I saw this hand first. Please introduce yourself.
I'm Sasha from Australian National University. Could you please go back to the slide where there is a compiler inserted bounce check? And yeah, so here I think the check is redundant. Will it be removed by the next optimization, or will it be present?
That's really a good question, thanks. So yes, in this example, the compiler optimization actually is able to remove this bounce check because it considers it's redundant. So for this, we worked with the compiler backend team to implement the LLVM path called constraint elimination that exactly tackles these issues.
Hi, thanks for the great talk. I'm Yeoul Na from SNU. So in your talk, you mentioned about the way of fixing the memory problem in C++ code by adapting the more memory-safe languages like Swift or Rust. But recently in C++, they're aggressively adopting new memory-safe types like spans, string views, smart pointers, and stuff like that. And they argue that just like rewriting the code in memory-safe languages, they can actually rewrite the code in more memory-safe types incrementally. So, and they argue that they can achieve the same goal using this approach without fiddling with other languages other than C++. So, what is your opinion about this approach?
All right, thanks for the great questions. So here I just shown you the C extension, but we also have a safe purpose model for C++, which exactly uses safe span types for instead of raw pointers for memory accesses. But the thing is, span types doesn't have lifetime. The C++ spans don't have lifetime guarantees, whereas Swift or safe languages have lifetime guarantees. Also, string view the same. So, like for C++, it's the same, like similar situation. Although it has more safer abstractions than C, it doesn't guarantee memory safety properties by default.
I think we'll do one more question while we switch laptops.
Yeah, hi, thanks for the nice talk. Ralf Jung, ETH Zurich. Also, thanks for those compiler passes, because Rust also greatly benefits from those, I think. So speaking of Rust, one thing I was wondering is Swift and Rust both are talking a lot about C++ interop right now. Have you given any thought to Swift and Rust interop and whether there's anything interesting we could do there? Because they are both languages actually are safe already, just not in exactly the same way, but still that should be useful somehow, right?
Yes, so I'm not here to compare these languages, but I think the same approach can be also applied to Rust. And I know like Crewbit project is trying to do something similar. But I think the key difference, just my own knowledge, is that Swift supports interoperability as a first-class language feature. So Swift compiler directly imports C++ headers, and it understands C codes because Swift embeds a claim. So in that way, I think it's, my own opinion, is more convenient to interoperate with C and C++ with Swift.
Okay, thanks.
All right, let's thank the speaker once again.